You're full screened and everything.
All right, and we're recording. So, going to be talking about PEGKit today. Um, so PEGKit is a parser expression grammar. That's what the PEG stands for. And this is an Objective-C framework. So going to be seeing a little bit more Objective-C, not a whole ton, but some. And this provides string tokenization using these two classes as helpers. And it also generates static parsers with grammars. And these grammars are BNF style, or you say it Bacchus Noir or Bacchus Noir. I'm not sure how you said it, but that's just like the writing style of the grammar, and which is similar to Yak or Antler, if you guys have heard of either of those. And Yak has been around for a long time, I think. And Yak stands for yet another compiler. And I'm not sure what Antler stands for. But Antler is kind of the Java and C# version. So if you wanted to build grammars, in either of those languages, that's what we use. And for this particular framework, it also provides callbacks. So you'll like match a rule, and we'll talk about those rules. And you can call a callback in your parser code. So this is created by Todd Dittendorf, iTodd on GitHub. And Todd originally created a framework called ParseKit instead. So PEGKit is kind of like the second generation parser that he created. And so if you go looking online, a lot of the stuff you'll see is actually on ParseKit. And ParseKit is more of a dynamic parser, and it has kind of has exponential performance characteristics, which means basically the larger your input gets, the slower it gets. And then so he decided to switch to PEGKit, which produces a static parser, which has memoization, and you just compile that directly into your project. And the good thing about this is it has performance. So the bigger it gets, while it may get a little slower, it's not terribly noticeable. So the main thing that you're going to be working with is a grammar, and this grammar kind of defines the domain-specific language. And so an example grammar could be anything from just like a little math grammar, plus, minus, divide kind of stuff, which that's the grammar we're going to be building today, or all the way to like C# or JavaScript. So within a grammar, each line is a rule. And here is an example rule. So on the left-hand side here, we have the name of the rule, which is Atom. And it's named Atom because it's just kind of like the smallest molecule or whatever for our grammar. And then on the right-hand side, you have what the rule's value is. And in this case, it's going to be a number. And this number is special in that it's capitalized. And within PEGKit, that represents a built-in value. And then it's always terminated by the semicolon. So some of the other built-in values are words, quoted strings, numbers, symbols, white space. And of course, you can combine rules to create more complex definitions. So, and a rule can repeat like 0 more times or 1 or more times, kind of like regex with the star and plus. So here's a little bit more involved. And by looking at this, can anybody guess what this does?
So you're setting up what numbers are and then what the plus is, and then you have that expression to what those you're proposing those together into an
Yeah. Yeah, so we're just defining this DSL to say, how do you represent adding two numbers together? So PEGKit will parse this grammar from the top down. But for smaller grammars, I sometimes find it's a little easier to read it from the bottom up. So if you look at the bottom, there's our atom, which is a number. And then we have our plus atom, which has the character literal of plus. And so whenever you type something like this, it means like look for this exact character. And the bang here represents when you go to tokenize this data to not include this specific character within the tokenization. So we're saying look for the plus sign, and then the atom rule, which is a number, and then the add expression, or the add expression rule, is the atom, and then the plus atom rule, 0 or more times. So this should match 1 plus 1, or 2 plus 12 plus 3, so any numbers like that. So let's take a look at what that looks like in actual code. I want this guy. So first thing I want to show you guys is the actual tokenization. So on line 30 here, we're defining a string. So it's 1, 2, 3 blast off, and that's in quotes. And that also has some characters in there that would be considered symbols, like the bang sign. That's considered a symbol. We got some commas, some words, and then we have some white space and the double slashes, which represents comments. So built into PEGKit is it knows about comments, and you can configure, what those comment characters are and things like that. Let me go ahead and run this. And so you can compare the code with the output here. So we're building that string, and then we're initializing a tokenizer, passing it the string, and then we're just getting this end of file token here, and then we're doing a while loop on the tokenizer, just saying give me the next token, and then print out the description. So looking at what I printed out here, we got it's 1, 2, 3 blast off, and that was the quoted string. And then the symbol for the commas and words, and a look here, so there's the she said, and the symbol goes directly to a symbol, well, the symbol and then the word and. So you can see that it completely skipped this comment. And then, so the same thing with the quoted string. And notice this one is using single ticks instead of quotes. And then just words and symbols. So at the core of PEGKit, it's kind of using this tokenizer and pulling all these tokens out of the grammar. So let's take that example grammar I showed you. And the way that you generate a parser is you can pull down the PEGKit source code. And so here I pulled that down, and they have this parser generator application. And so I have that running here, built that and have that running. And I basically just paste your grammar into here and then hit generate. And so we have a little bit of configuration here, like where it's going, the name you want to call it, and then you can configure whether you have pre-match callbacks or post-match callbacks. So we're doing post-match callbacks, and then here's our grammar. So just generate that guy, and then we'll go back to the project here. So that generated this expression parser. And here it's from the PK parser. And typically you don't ever have to jump in here unless you need to debug stuff. But it is kind of nice. You do have the source code here, so you can debug through this. The main thing you may want to know about is this self fire delegate selector parser did match Atom. So this is that callback that it's creating for us. So I created a class here. It's called Simple Math, and it has a parse function, and it returns this PK assembly, which is a PEGKit class, which is going to represent like the output from the parsing. And so in the implementation here, create an instance of the expression parser, and then I'm parsing the string that's being passed here, and then just print it out in case we get an error. And then here's the implementation of our callbacks here. So did match Atom and did match plus Atom. So those were our two like primary rules that we saw here. So we had that, plus Atom, and then just Atom. So let's run this here. So and I created this little UI where you can type in numbers to add. So let's do like 1 plus 1 and hit calculate. And if we look in the output down here, so this is just printing out the matches. So what it did is it matched. Actually, let me switch this to make it a little more clear. That makes it a little more clear here. So first thing it matched is the 1. And then it called did match Atom again. And you'll see this 1, 2. And then you see it got the did match plus Atom. Now this syntax here, what this means is these ones in the brackets here, those are the current items that are on the stack. So when you're doing a parser, you're kind of keeping track of what stuff is kind of currently in memory and what you're currently parsing. So by default, what what PEGKit does is that if you parse something but you don't do anything with it, then it's just going to keep on adding it onto the stack. So with our input here, it hit the 1 first, and that is an atom. So there we hit that. And then the way that the parser works is that it's recursively going down the tree. So the next thing that it would match is it would match the +2, which with the match plus atom rule. But within the match plus rule, there is atom, right? Which is the number. And so it would hit the atom callback first before it came back to match the plus atom callback. So that's why you're seeing that there. But if you look, so here's kind of that same output that we saw in the console there. But this right here, this is supposed to be our result, but we just got 2. So and so why did we just get 2? Because we're building this like plus grammar or this math grammar, right? So look at the implementation here. So here's like the click event here. So we're going to say calculate and then display the input of what we entered. We're going to create our simple math class, do the parsing. We're going to get the description from the assembly. And then we're going to pop a token off from the stack of the assembly. So the PK assembly represents the stack and the result of the parse. And so we're going to set this first token that we get, whatever it was, as the result. And then we're going to set this other stack label to the description that we got from the assembly. So if we look at this, these brackets are what are currently on the stack. So that's 1 and a 2. So when we popped a token off, we just got the 2, and that left the 1 on the stack. And so we're just displaying a 2. So basically, all we're getting right now is still just like glorified tokenization. So we need to find this grammar, but it actually isn't doing anything yet. Right? So we need to actually implement what happens when you match this rule. So let's do that real fast in our callback here. And we're going to do this in the match plus atom. We'll just paste in some code here so I don't fat finger it. So when we hit this match plus atom, then I'm just going to pop a token off the stack of the assembly, which we're getting passed in here for us. And when you're popping stuff off, that's going to go from right to left. So in our example of 1 plus 2, this right token is going to be 2, and then we're going to pop it again. The left token is going to be 1. And then I'm going to convert these tokens into their actual number value. And then I'm going to push that back onto the assembly stack. So here, when I popped 2 items off, now the stack is empty. And then I'm going to convert those numbers and do the needed plus operation, right? And then push that value back onto the stack. So now this should add those numbers together for us. So now when I can type do 1 plus 2, you can see the result is 3 now. And looking at the text description here, 3 was all that's left onto the stack. And then I should have mentioned this before, but this syntax here is showing how it was tokenized. So there's a 1 token, the plus symbol token, and the 2 token. And the caret represents like where the cursor currently is in parsing. So the parser got all the way into our input, and that probably did that. So if we did this right, we should also be able to do another number, get the result, and 3 plus 12 is 15. So that looks right. So that's kind of like really basic introduction to how you can build a little simple grammar and use that here. So now we can look at a little bit more ways that we can use this. So talked about this a little bit, which so the parsers, they're recursive descendant, so it goes from top to bottom, and then when you hit a rule, it goes down the rabbit hole, of that rule, and then comes back up. So kind of like traversing the tree of values. It's deterministic, so you can kind of know what is going to happen before it happens, basically. It's memoizing, so it's smart on how it's going through the tree, and it has infinite look ahead, which is nice because maybe your rule may do certain things based on what the next value is. It's predicated here, which basically just means you're able to insert Objective-C code directly into the grammar syntax. So and that's what I'm going to be showing here in a bit, where instead of writing that code in the actual Objective-C member file, you can just add that to the grammar itself. And then I kind of chuckle at this last one, because these are some of the bullet points that he has on his site. It's written in modern Objective-C, in blocks and art and properties. But I kind of chuckle at that now because the new modern Objective-C is Swift, right? So even though he actually just started this rewrite, I think late last year or early this year, so it is actually pretty new. So we looked at that PK assembly, and I should disable hip chatting. So PK assembly, it has the stack and talks about kind of the buffer of the tokens that matched for the parsing input. And then here's just kind of help for that syntax again here. So stack contents, the match tokens, and then the caret for where the cursor is. So grammar actions, this is what allows you to add the Objective-C into the grammar itself. And I'm going to show you the not so good way to do it, then the better way to do it. So let's go take a look at that. So I'm going to go back to my simple math here. Pull out these guys. And then get oh, well, first of all, let's update our parameter here to add some of the other math operations. So here we have our atom again. That's the number. And then we're just adding some rules for multiplication and addition, and adding the ability to add precedence via precedence. So if we look at this primary rule, this is saying it's a number, or it's an expression that has parentheses around it. And here we have the bang to say, I don't care about the parentheses, but they need to be there to be able to match this. So then the multiplication expression is a primary expression with a the times symbol, star symbol, and then the primary again, and we have the star, meaning this is going to be repeated 0 more times, and basically the same thing with the multiplication. And notice this is the thing that I think is really interesting, is that up here, this EXPR, this expression rule, either can be referenced all the way down here, and so.
So does the order not really matter then when you're like defining your grammar, like the line orders in there?
So
yeah, like in the previous one, it really made sense when you read it from bottom to the top, but now you're like using expression before it's even defined, right?
Right. Yep. Yep. And so that's why it is technically, descendant parsing, right? So if here you kind of do have to read it top to bottom. So okay, expression is add expression. Okay, well, what's add expression? Add expression is this multiplication expression. And so what's multiplication expression? Okay, that's primary. Okay, well, what's primary? Primary is an atom or this. And what's an atom? So yeah, once you start getting into a little bit more complicated ones, you really follow how the parser is going to interpret it. You kind of do have to start from the top. So there's a little bit more complicated one. And now let's add some grammar actions to this guy, so that we can implement these math functions just within the grammar here. So let me pull that up here. All right. So now we actually have some Objective-C code in here. And let's look at this atom one, since that's kind of the most simplest one. So we're kind of doing the same thing we did before, where we're popping off the token, and here we have access to that assembly object, and this is just an assertion here. Make sure that it is a number, and then we're getting the double value from the token, and then we're pushing that back up to the stack. So this is converting it from basically a string, or well, I should say, it's converting it from this PTake token class to an NS number. So it is an actual number versus this like token class. And so let's assume that our input that we were using is at 1 plus 2. So going to this add expression, we're doing the same thing, popping off the 2 tokens, and then doing our addition there, and then pushing that value back on there. And the multiplication looks exactly the same. Only difference is the time symbol here. And then we don't have to do anything with this primary expression because all this represents is the parentheses. So let's generate that guy. And if we look at that generated code, that just got a little more complicated because of a little more rules that we got in there, right? So, but none of this other code needs to change. So we'll run this, and let's make sure that our existing stuff still works. So 1 plus 2 is 3. And then if we do times 2, what's that going to do? Okay, so notice that this is smart enough because of the way we wrote our grammar that this is correctly using math precedence, right? So we got 2. It first evaluated 2 times 2, and then added the 1.
And that's really just because the multiplication line was before the addition line?
And not because it was before, but it was because if you look here, the addition line is actually before the multiplication, like in...
Well, before top to bottom, right? The multiplication expression is first. Oh, you're right. Add expression. No, yeah, I see.
Yeah. So add expression is defined first, but add expression is built from multiplication expression.
Oh.
And so it's going to evaluate this guy first before it goes to the addition. And so I think this is what really shows the power of what the grammar is. Because that seems like a lot of work, right? Well, I can go write a math, math, times and addition and stuff pretty easy, right? But it's like precedence things that the grammar, using the grammar really starts to shine through. So, I could go do things like this, and this should work. So, what we expect this to be. So, oh, and now, other messages. So now I expect this to be 3 times 2, so 6, right? And so now it's kicking in, this primary expression with parentheses. So it's going to evaluate that by itself, until it goes to another one. So, but look at this. This seems kind of blah, right? Now I have this Objective-C code in my grammar, which I can't really compile here, and there's just a lot going on. So luckily, it provides a way to make that better, which is through these macros. So you can pop and push values off the stack just using the macros, and that makes it look a lot cleaner. So for instance, this pop double. So I'm going to pop a double value off the stack, and then I can push a double back on the stack using the macros. So let's see what that looks like using macros instead. All right, so this looks quite a bit more clean. So, and a lot easier to read. So in our add expression, we're going to say we're going to pop a double off the stack, add it to another pop double off the stack, and then we're going to push that double onto the stack. And the same thing with multiplication, just with times. And the number itself, we're just popping the double and pushing a double as well. So if we generate that and rerun, type for symbols today. So there we got our 3 times 2, and Preston's still works as well. So pretty cool stuff.
Are those built-in macros, or can you define your own too?
Those are built-in macros, but yes, you can define your own. Like for instance, just with inside the grammar, there are like special actions. I can actually pull up the website here. Yeah. So like these are all the also actions you can do. So you can say to like insert additional objectives code into the generator file. So like, oh, I want to add a property to the header file. So you can use the add h and add a property. You know, and then you can add some other stuff like with the initialization. So let's say you wanted to keep track of like some other data like throughout the parsing, and you have like so I'm going to define a list, and have that list available outside the parser, and then but I need to initialize that list, so I'm going to initialize that within a function here or something like that. And it also has like macros such as this ls, which is look ahead string. So like for instance, this here it's saying so look ahead to the next string. Look ahead to the next thing. Convert it to a string, and then look at the character at that index. So you can get to some pretty complicated scenarios without too much code. So I was bad and I didn't check when we started. About when did we start?
45.
About 40, yeah, about 45. This grammar that I've been showing you is pretty, it's the simplistic one, right? So just doing math and adding and removing just numbers to and from the stack. But kind of a more advanced scenario where you would typically be using this is when you're doing this parsing, instead of just adding simple numbers back onto the stack, you would instead do what they call build this abstract syntax tree. So which is a tree representation of the domain-specific language. So let's say, for instance, like if you were doing like a JavaScript grammar, right? Let's say you had a rule for what a variable looks like. So that would be like var abc2 or something like that. So you would parse that out, and then your rule would catch that var abcd, and it would say, oh, I know that this is a variable, and so that variable has it has a value, and that variable could be referenced elsewhere in your input string, right? So you say, var abcd equals 2, and you could say abcd equals 3. And so you're going through the parser, like you would create a class that represents your variable, and maybe it's like current value. So that's just like an example. And so this one thing where PEGKit falls down is that if you want to build this AST, you have to do that yourself. Whereas other frameworks, such as Antler will build the AST for you as well. And so, hopefully someday PEGKit, will implement that for you. But building this AST yourself isn't terribly hard. It's just a little time consuming. So you just have to build all those classes yourself and make sure you're popping stuff off and putting it back on yourself. So that is basically what I have for a little introduction. But if we did have the time, I was going to try and start coding like this abstract syntax tree, if you guys were interested. But that's pretty much what I have. The main links here are PEGKit. It's just up on GitHub. ParseKit.com. That's the dynamic framework. But a lot of the concepts and even like the grammar samples still apply. And this has this PEGKit mini math tutorial that kind of goes through basically what I went through with you today.
And I've been wondering, like, I can see this being super cool for like someone that's writing their own compiler and stuff like that. But besides that usage, what other usages? I guess, are there any hardcore PEGKit users that use it for, I don't know, something in like a company or something like that to make money or something?
So yeah, like one of the main usages of something like this would be basically anywhere you would have like raw user input that needs to represent specific data. So two main examples I can think of is, they're not necessarily using PEGKit, but they're probably using, PEGKit is kind of like the only guy in town for Objective-C. So I have seen some other small ones, but PEGKit's kind of like all that's out there for the Objective-C side of things. But Antler, for like Java and C#, Antler, it's much more mature and used like a lot. And the examples of where it would be used is I read where people created grammars for like SQL, right? So somebody built an application where you're able to query, like the SQL database, but they wrote like their own custom application, and so that you can.
Well, that's exactly what NHibernate does. They use Antler for their HQL.
Yeah.
syntax.
Yeah. There you go.
Yeah, and like even Raven, they have their own little syntax.
Exactly. Yeah.
They could use something. They probably use something.
Another example would be
You try the search.
search stuff.
Yeah, search stuff to like tokenize it and have keywords and things like that. Another example would be if you guys have ever worked with any like reporting tools, where you would enter in like variables, and so you could more easily be able to like tokenize that data, using like a specific grammar. And it's especially helpful when there are it's like if it's like a very strict language. So if you go on to just their website here, he has a bunch of like example grammars. It's like here's a grammar for CSS. So you can build the a parser for CSS using that. There's grammar for JavaScript. And he did have on here before, but I don't see it anymore. Where he had both JavaScript and code for JavaScript. So it's a little bit different. There's ones for C. An HTML grammar. And these are just kind of like example grammars. Even a grammar for Objective-C or regex. That's one thing I didn't mention, but like you can customize the rules so you're not just limited to like just match on a word or something like that. You can say match on this regex. So like here's a grammar for SQLite. And so the hard part is though. You have to build that abstract syntax tree, and then determine, what to do with that syntax tree. Like how do you execute, this this line of stuff. And so that's kind of what I'm actually using this for right now is an application I'm building, which has like a custom scripting language. And so instead of me trying to parse all that out myself, I'm using this so then I can more easily build that syntax tree and then execute those script lines. So before I started looking at this, I wasn't sure how often it would be used, but just some of those examples you guys talked about. I think this sort of stuff is actually used quite a bit. This probably wouldn't be like my first thought on what to use, but like building a grammar to just like parse a CSV file or something like that, that makes this like stupid simple. I mean, it's just like a few. I think. Well, here's like an example. I think this one's from Antler. Go out of presentation mode. There we go. It's like this is actually like an Antler one, but like this is a CSV grammar. So then you can just define this grammar, and it'll do all that parsing for you. So you don't have to worry about the quoted strings and the commas and whether it was an actual comma. Maybe it was a different delimiter or something like that. And you can just define all that in the grammar instead of trying to write all that in the code. So, anyways, that was a great question.
Good answer.
All right, well, that's it.
Thanks, Joe.
Thank you, Joe.